All right, I do not know how that happened, but everybody type in the chat box again so that I get your attendance. And I'll have to see what the heck happened with the setup of this, because I use the same settings. So let's try that again. So we've got two different formulations now for population growth. One for discretely reproducing populations. That's the geometric growth rate. So n at time t is equal to n at time 0 times lambda to the t power. We also have a formulation for continuously reproducing populations, where there is no discrete period of reproduction. Like it's just like us, like bacteria. Those are the examples that everybody relates to. And so that is similar but not identical because it has to be exponential. It's n at time t equals n at time 0 times e raised to the RT power. Well, that's great. All right, so we know how populations are supposed to grow. But here's the problem. We don't have a realistic depiction of nature yet, because all we can do with those equations is model populations that grow infinitely, that never stop growing. And the reason is because our growth rates, either lambda or r, are constants. So you multiply some number of individuals by that growth rate and you get more individuals. You multiply the extra individuals then by that same growth rate, you get even more. There's no way to cause population growth to slow down or stop. So you can get either infinitely growing populations or populations that decline to extinction. But right now, we have no way to describe what really happens in the real world. Even though elephants reproduce very slowly, if there wasn't something that checked the population growth of elephants, we'd be up to our armpits in elephants very quickly. And we know that we are not. So we have an incomplete description of nature. And that is why we need to tweak our equations to account for something called density dependence. Now, density dependence is an important concept here. It helps us actually model real populations in the real world that don't grow or decline infinitely. For convenience sake, we will tend to work with not the geometric equation, but the exponential growth equation when we talk about density dependence, population regulation, and even when we move on to interactions between species. Now, I want you to understand there are formulations for both of them, for both the lambda formulation and the little r formulation, but why complicate things? We can make the point using only one of them, and there is a convention in ecology that the growth rate modeled by r, that is e to the RT, is easier to work with in many ways. So for the most part, we're going to focus on developing equations from the exponential growth equation. And at time t equals n at time 0 times e to the RT. Okay. So having said that, this is what we're going to cover today. We'll talk about exactly what we mean by density dependence. We'll give you examples of positive and negative density dependence. We'll talk a little bit about how density dependence in discrete populations would look. We're not going to focus so much on the equation itself. What we're going to focus on more is what the graph of population growth would look like and how it would change. Then we'll move on and talk about the continuous population growth, and we'll derive the logistic equation, which is the basis for about the next month and a half of ecology. So let's let's try to get back here. There we go. All right, so what is density dependence? A density dependent factor is anything that affects population size relating to its density. So it doesn't have the same effect on small populations as it would on large populations. Its effect is dependent on the density of the population. So it could be weak on one extreme and very strong on the other. And we will have examples of this for you to think through. So density dependence then allows us to consider how population growth might be checked. And in particular, in ecology, we are going to focus a lot on factors that show negative density dependence. That is, that as the population grows, something opposes that growth. Okay, and negative density dependence is described by real populations, because if a population that is growing slows down and becomes stable, then by definition, the growth rate of that population is density dependent. It would be a fast growth rate at low population densities, but when you get lots of organisms, it would slow down and stop. So that would be negative density dependence. And that's what we need to explain in nature. That's what we need to derive an equation for. So the most common things that produce negative density dependence in real populations are things like resources, limiting resources, competition for food, competition for nesting sites, the physical space occupied by organisms. The more organisms there are, the more competition there is for food, the more competition there is for nesting space, the less physical space there is for organisms to occupy. So I think you can see that I just identified two things that have positive density dependence and one thing that has negative density dependence. Competition for food and competition for nesting sites increase with density. That's positive density dependence. The amount of space available for each organism decreases with population density. That's negative density dependence. The effect of these three factors, though, is to produce populations that show negative density dependence in population growth. As the population size increases, organisms have less and less access to resources. Remember from life history, the principle of allocation means that if you have energy, you can only devote it to certain things. You cannot simultaneously devote it to everything. And if you cut the energy budget, that means that something has to go. Either you're going to survive less or you're going to reproduce less. Well, both of those things would cause negative density dependence in population growth rate. They would cause the population to slow down its growth rate as you get higher and higher densities. Okay, so if you get too many organisms, competition, regardless of whether there's anything else in the environment, competition for resources will cause that population to stop growing. There are other things that would factor into producing negative density dependence in population growth, and those are things like diseases, which are easier to transmit in large populations. Humans did not have most of the communicable diseases we have today 10,000 years ago because we were just starting to settle down in communities and increase our population through agriculture. Hunter-gatherers have very few diseases. They simply can't support transmission because they're just not enough people. Predators, Large populations produce attraction to the predators of those populations. And any of you who've ever ridden a bus that was crowded at rush hour or taken the subway in a big city during rush hour know that simply crowding can stress you out. And stress depresses reproductive output. So there are a lot of reasons why populations stop growing. And I'm going to get rid of this live transcription because it's in the way. I want you to see that. So how do I do that? Not sure I know how to, well, I'm not sure I know how to do that, but this is really annoying because you need to see that. Not subtitle. Hide the subtitle, there. All right. What we say, I'll put them back on. What we say is that when a population reaches the limit of what the environment can support, so the number of organisms or the density of organisms in a given area that the environment is capable of supporting, and it becomes a stable population that doesn't continue to grow, we say that it has reached its carrying capacity. So the number of organisms that the environment can support indefinitely is called K, or the carrying capacity. And we're going to use K to make our population growth equation more realistic. We're going to have it factor in so that we can cause populations to stop growing when they reach, so I'm going to show that again now, when they reach the density that the environment can support. All right, so the carrying capacity then is set generally by things like competition for resources. And competition acts as a check on population growth. So I think you can see right now that we have kind of this issue. It's because we're saying that R and lambda are constant. And yet we still need to have a way to make them stop causing the population to grow. So we're going to have to use this K somehow to force that to happen. Okay, and that's going to be the end of this lecture. That will be the logistic equation. All right. And it's not letting me advance. There we go. All right. So let's talk first about negative density dependence. Okay, and these are some of the most influential experiments that have ever been done in ecology, and they were done by relatively few people. But here's one that sort of kicked off the whole process. Raymond Pearl, back in the 1930s, was working with fruit flies, and he introduced different densities of fruit flies into bottles with limited amounts of food, and he found that some of the bottles allowed that population to grow if it was a small population, but other bottles quickly exhausted the food and the population declined. Okay, and what he did then was say, oh, well, what exactly is going on? And so what he did was measure the number of offspring that the flies were producing. And he also looked at their survival rates. And he said, okay, what is influencing the populations in these bottles? Is it more that the animals are dying, or is it more that they're not able to reproduce? And what he found was both were happening, but in a really interesting way. So on the top graph here on the right, you see two lines, and the green line is the reproductive rate, the number of offspring per fly. And the purple line is the number of is it days? Yeah, number of days that the adults survive. And so what you see is that the green line plummets very quickly. As the population grows, reproduction starts to decline very quickly. As the population grows, so does survival, but notice that reproduction declines before survival does. So, how are these flies allocating the limited amount of energy that they have to work with? Well, very clearly, if reproduction declines quickly and survival declines slowly, they're trying to stay alive as long as possible. They are sacrificing reproduction in order to stay alive, hopefully to reproduce in the future. But that's what the shape of these lines indicates. And that is an important lesson. Animals prioritize survival over reproduction because dead guys don't have sex, basically. So that makes abundant sense. Now, a second study in ecology was not an experimental study like Raymond Pearl's. It was an observational study that about 50 years ago became very influential. And what people did was monitor the population sizes of birds that were colonizing islands off of Massachusetts. And so at the bottom, you see that you have 3 different islands being colonized. And you see that these birds, these terns, colonized this first island, Bird Island, in the orange very quickly. And then what happened? They reached a stable density on that island of about 1,600 birds. And after that, the number of birds did not continue to increase. They were limited by the number of nesting sites. And so they quickly reached their saturation. And what this tells us is that despite the fact that these are growing populations, they cannot grow indefinitely. They will eventually be limited by competition for something. And in this case, we know it's competition because there are no predators on the islands. There are no diseases that were recorded. It was competition for nesting sites. Okay, the second island in green here, Ram Island, also showed a really sharp increase initially, but then kind of stabilized. And this doesn't go out long enough to show you that it became truly stable. It still looks a little bit wonky over there. So these dots here are not as stable as the orange dots, but the population did not continue to grow. And when that second island reached saturation, they moved on to a third island, and you see the same pattern, kind of an exponential increase in numbers. And it didn't go long enough for us to see it become saturated. But you see 2 things about this. Number 1, populations that are not limited by competition show this really beautiful upturning curve, the same curve that we posited would be seen in either geometrically growing populations or exponentially growing populations. The curve starts shallow and then gets steeper and steeper. But we also see that it doesn't do that indefinitely. Competition does limit the growth of these populations. So competition causes then negative density dependence. We can see it in the bottom graph, and we can see exactly why in the top graph. We can see that negative density dependence in population growth occurs because when resources get scarce, animals stop reproducing. If they get really scarce, some of the animals may die. But there is a limit to reproduction. And it's produced by competition. It can be produced by other things like diseases or predators, but even if those didn't happen, populations could not grow indefinitely. So let's now talk about something called positive density dependence. This is a fairly rare phenomenon when we're talking about the population growth rate. Factors that affect the growth rate are frequently positively density dependent. Competition increases with population size, right? So competition gets stronger. That's positive density dependence of competition. But the growth rate itself, we've been saying, has been typically high in low populations and low in dense populations. So we've been talking about negative density dependence of the growth rate. However, in some species, that growth rate shows positive density dependence. The more animals you have, the higher the population growth rate. And here's an example. Okay, so here we have something called the Ali effect. And that's where a small population finds it difficult to reproduce. So the population growth rate is very low in these small populations simply because there may not be enough, in this case, flowers for bees to pollinate. And so a lot of flowers go unpollinated in small populations. In animals, you may have a lot of trouble finding a mate in a small population. And as the population grows, you have more opportunities to find a mate. So the birth rate increases as the population grows. So these low densities then are associated with very low population growth rates. And as the population increases, so does the rate of population growth. And this little graph down here in the bottom right illustrates this. At small populations, this little plant, the cowslip, has very few seeds produced. And you can see that some of these points are zeros. So at small population sizes, sometimes this population can't reproduce at all. And the larger the population, the higher the growth rate, the more seeds that are produced. And this is simply because pollinators are attracted to large aggregations of flowers, and they tend to miss flowers that are isolated. So here's a good example of positive density dependence. Now that's a problem for species because if you fall below a certain size and your population growth rate starts to decline, it's going to decline so that your population in the next time step is even smaller and your growth rate is even smaller. And so this is a spiral to extinction. So species that show positive density dependence have to maintain population sizes that are above a certain minimum. And this is a common problem that we work with in conservation biology. A lot of assisted reproduction programs in conservation biology are designed to address the issue of the Ali effect in a population of conservation concern. There are just too few individuals for that population to reproduce well. Okay, now you're saying, well, okay, so we have negative density dependence that limits the growth of the population. How can we have positive density dependence? Wouldn't cowslips here then grow infinitely and we'd be up to our armpits in cowslips? Well, it doesn't work that way because eventually even species that show positive density dependence at low numbers will show negative density dependence at high densities. So here's how that looks. So here's a population that is regulated by both positive and negative density dependence in the growth rate. At low densities, on the top right here, you get an increase in the growth rate because it's easier for organisms to reproduce. But once you get to a certain density, then competition starts to work its magic and the growth rate starts to decline. And so you should see something like, maybe not a bell-shaped curve, but you should see a curve with an intermediate peak of some kind, even in populations that have the Ali effect at low densities. And on the bottom, we see an actual population that shows exactly that. These are adult herring, and this is the ratio of young herring to adult herring. So the higher this number is on the y-axis, the more babies there are relative to the adults. And what you can see is that when herring populations are really low, there's not a lot of reproduction. That's down here. And that means that small herring populations don't reproduce well. As those populations get bigger, they start to reproduce a whole lot better. And then as competition kicks in beyond a certain density, reproduction starts to become more limited again. And so you have the curve that shows the intermediate peak, high reproduction at intermediate densities, low reproduction down here because they can't find mates, and low reproduction over here because of competition. So competition and needing to find mates, that can cause a lot of species to show this bell-shape-ish curve with an intermediate peak. Okay, for the most part, for the purposes of learning about population growth and density dependence, we're going to try to just assume that positive density dependence isn't working in the populations we're going to work with. We're just going to say, okay, the population growth rate is going to be constant for all populations that we want to model. We're not going to have this bell-shaped curve. We're going to have a steady decline from high reproductive rate at low populations to low reproductive rate in dense populations. And we have a question. Jason. Okay, so what Jason is asking is, over multiple generations, will that bell-shaped curve here on the bottom start to look like a wave? Well, what you're kind of getting at is what the life table might look like in a population like this. And yes, you could very clearly see big increases in numbers of certain age classes. If you just did a static life table where you said, let's take a snapshot in time and see how many individuals are in each age class here. If you have a population that goes through cycles of low population density and high population density, you're going to get one of those weird static tables where you're going to start out with 1,000 babies in one, say, 1,000 newborns at a particular time, and yet you might have 1,200 one-year-olds because the population was really at the optimal intermediate point the previous year. So yeah, that can generate lots of fluctuations in how many individuals you have in a particular age class. This particular thing here also can produce oscillations in the population size itself. We're going to defer that to tomorrow. And I hope at least one person is here in person because I don't want to be here all alone, but I'll be giving that lecture here tomorrow at 11. So those of you who can't be here, just tune in with Zoom, but somebody come, geez. All right, so populations that show this kind of behavior will show you a lot of fluctuations in numbers in the life table. They'll also probably show you a lot of fluctuations in population size over time. And we have dealt with the first one already. We'll deal with the second one tomorrow. All right, so let's look at what discrete population growth might look like if we have density dependence. So here is on the left our graph of unlimited geometric growth. And so you see you have a steadily increasing curve. The population starts small and gets big. Okay, and the problem is that we know that that can't go on forever. So what has to happen? Well, somehow lambda cannot remain constant. Something has to force lambda to decline as the population size increases. Now, as I said, we're not going to spend as much time on the discrete model as we will on the continuous model, but in the center, you can see what we imagine has to happen to lambda. So lambda can start out high at low numbers, all right? And this is actually a tripling of the population in each time step. So that's really high. That's really explosive growth. But it has to decline as the number of individuals increase. And at some point, lambda will decline to the point where it reaches a value of 1. Well, a lambda of 1 means that the population is stable, because it's the ratio of population size at time t to the population size at time t, the previous, t minus 1. So if that's 1, then those two numbers are equal and the population has not changed. So we know that this has to happen. So what would it look like? What would our population growth curve look like if this is what actually happened to lambda? Well, this is what it would look like on the right. We'd see that initial exponential, well, not exponential, we'd see that initial geometric increase where you have the rapidly uprising curve, but as lambda declines to 1, the population would reach stability. And you would get the population stabilizing at its carrying capacity. So this is a little graphical model, a little graphical way to think about how geometric growth has to actually look in the real world. I haven't written the equation for it because it's complicated, and I don't want to do that. So if we look at the continuous growth model, you will see when we're done why we prefer to work with this. It's just easier to write the terms out. So the continuous growth model has to do kind of the same thing, except when lambda goes to 1, R has to go to 0. So how do we force R to go to 0? We have to have extra terms in there. And those terms have to be related to the carrying capacity. So we modify our exponential growth model using the term K. And what we do is devise a logistic growth curve. So the logistic model simply refers to a curve that is S-shaped. And that's exactly what we need this population to do. It needs to start growing exponentially, and then it needs to do exactly the opposite thing. It needs to slow down kind of exponentially and reach a stable number at the carrying capacity, K. Now we can do this with our d sub t equals, our n sub t equals n sub 0 times e to the rt, but it's a heck of a lot easier to use dn dt. Let's just talk about the rate of change. So we know that the rate of change should start off slow in a small population because there are not a lot of organisms reproducing. We know as the number of organisms reproducing increases, R times a bigger number equals a bigger increment in the population, and so the population growth curve will curve upwards in our exponential curve. That's this right here, this part right here. But at some point, competition then is going to start limiting the resources organisms have to reproduce, and that's going to wind up reducing the population growth rate to stability. So the way that we add this in is this little term here. We've already said that dn dt, which is the slope of this line at any given point, is equal to r times n. We've already said r is a constant and n is the thing that can vary. The number of organisms reproducing varies. Okay, but we can't allow this maximum growth rate to go unchecked anymore. We have to add a factor in to cause the overall change in the population to go to zero. So that is this 1 minus n over k. Now think about what that means. First off, it's equivalent to k minus n over k. Because you can factor out the k in the bottom, and you can have k divided by k, which is 1 minus n divided by k. And so this is the same thing as saying k minus n divided by k. Now what's the deal with that? Well, notice that this is a little fudge factor that we can apply to the population growth rate. When the number of organisms is really small, that's n, then the carrying capacity minus a really small number is almost exactly the carrying capacity. And so you're multiplying r times n by a number that's approximately 1. And you get maximum population growth. But as n gets bigger and bigger and gets closer and closer to k minus n gets to be a smaller and smaller number. So k minus n divided by k gets to be a smaller and smaller fraction. If your k is 100 and your n is 2, then this term means 98 divided by 100, which is almost 1. But when you get really close to your carrying capacity, let's say you reach 90 individuals, 100 minus 90 is 10 divided by 100. So you'd be multiplying r times n by 0.1. And sure enough, that's going to cause this population to stabilize at some point. When n equals k, when the population has reached its carrying capacity, then the equation simplifies to k minus k divided by k. Well, k minus k is 0. And 0 divided by anything is 0. So you'd be multiplying r times n times 0. And remember what dn dt means. dn dt is the change in population over time. So the change in population would reach 0. And the growth of this population would cease. It would fall to 0 here, and you'd reach the carrying capacity. Now, we have two formulations. Trust me on this, okay? The exponential equation here, dn dt equals r times n times k minus n over k, I'm probably always going to say k minus n over k, is the simple way to think about it. What you've got here then is a constant growth rate, little r. You've got a variable number of organisms reproducing, that's n, and then you have the fudge factor, k minus n over k, that forces population growth rate to go to 0 due to competition for resources. So our curve is going to look like an S, regardless of whether it's geometric or exponential growth. We're going to sort of put aside the geometric growth in much of what we talk about over the next month and just focus on these exponential models because they are so much easier to work with. So this is the logistic equation. This produces an S-shaped curve. dn dt, the rate of change of a population size over time, equals R times N times K minus N over K. Okay, and the K minus N over K is part of the growth rate functionally. We write it as if it's next to the N usually, but it's actually part of the growth rate R. That allows us to keep the growth rate a constant. Little r, we can say, oh yeah, that's constant, but here's how competition would alter that growth rate. K minus N over K. Now, it's important to understand, to be able to visualize how that slope changes and how that's related to the change in the growth rate. So here on the top, we have the rate of population increase. Oh, no, wait a minute. I'm sorry. This is, yeah. Yeah, this is the overall rate of population increase. And this is not the label of the axis. So this is not the axis label. The axis is actually the number of organisms in the population. But this is the title of the graph. So don't be confused by that. So this is dn dt, the rate of change in the population, and here's the number of organisms in the population. Remember, we're assuming that we're not having an Ali effect where we have positive density dependence. You'll see that on the bottom graph. But here, because the number of organisms is small, you have a relatively small growth rate. As the number of organisms increases, you reach a maximum. And then as competition starts to take over, the growth rate of the population starts to decline and it reaches 0 at K. So when a population's at its carrying capacity, it's not growing. It's stable. So this is how, on the top graph here, the rate of population growth changes with the number of individuals. On the bottom is what actually happens to R. R steadily declines. And it declines from whatever the number is at a small population size down to 0 at carrying capacity. So this is what the population as a whole is doing on the top. This is what individuals are doing at the bottom. Each individual produces fewer and fewer offspring as the population size increases because resources are more and more limited. As a result, at the top, when you have few organisms, even though each of them is reproducing less and less due to competition as the population grows, because you have more organisms reproducing, you start out with a sharp increase. And at the inflection point here, we're over at K divided by 2, that's where competition starts to outweigh the increase in number of organisms reproducing. So you need to understand that R is a constant, but it is adjusted by competition. That adjustment is continuous. It's adjusted continually from a small population size and progressively gets smaller and smaller as the population grows. However, the population itself is growing because of increased numbers of organisms here until competition outweighs that. All right, so here's our closing slide. This is an example of how we apply this. We can simply manipulate the amount of resources and see, do populations behave the way they should? So here's a second really crucial experiment in ecology. Georgi Gauss, who also worked in the 30s, worked with paramecia. He put some in a container and gave them a certain amount of food and said, what happens to them? Well, you can see that these two species both stabilize. And the one on the top had a carrying capacity of 105 at low food supply, and the one at the bottom had a carrying capacity of 64 at low food supply. Then he doubled the amount of food. And he said, well, what happens? Not surprisingly, the number of individuals that the environment could support approximately doubled. At the top, you went from 105 to 195. That's pretty close. At the bottom, you went from 64 to 137. Again, that's pretty close. That's pretty remarkable. So populations actually do follow these rules. And this is an excellent description of real population growth in the real world where there's not unlimited amounts of resources. Now, in this presentation, we're not solving quantitative problems. We're asking you to understand what graphs look like. And we're asking you to be able to relate the logistic equation to those graphs. So the take home from this presentation is that we get leveling off at K for both geometric and exponentially growing populations. We will focus on the exponential version using dn dt to talk about the slope. And you need to be able to tell me things like, why is the slope 0 at carrying capacity? It's because K minus N over K is 0. So 0 times N times R is going to be 0. And the rate of change then is 0. They need to be able to tell me that populations grow relatively slowly at small sizes because there aren't a lot of individuals reproducing. They grow slowly at large population sizes because of competition. And they reach that sweet spot in the middle because there are lots of organisms reproducing and not so much competition that it's outweighing their reproduction. So this is now a more graphically oriented thing. We've been talking about solving equations, but now I'm asking you to relate the equations to the graphs and be able to interpret the graphs. This will be something we'll emphasize more and more over the next few weeks. We'll switch from doing calculations to understanding graphs. And I'm sure that's going to be good news for some of you and painful for others, but this course pretty much will find whatever vulnerability you have at some point. Okay, that's all we've got for today. So unless we have some questions, I'm going to sign off. I will see those of you in the lab at 1 o'clock. We will go out to the park and get wet if necessary and get those lab reports in.
Professor?
Yeah.
I know you just said it probably, but I was thinking about my question. For lab, are we meeting you in City Park?
Sorry?
Are we meeting you in City Park for lab?
No, the labs meet in 216 biology.
Okay.
I don't want you going to City Park without us talking about where we're going to meet.
Okay.
People get lost.
Quick question.
All right.
We'll have
anybody else?
Yeah. We'll have an online Zoom class tomorrow.
I've already got the Zoom set up. I will send you the Zoom link tomorrow. Okay, and if you can't Zoom, then you need to send me an email so that I record that you're going to get attendance later.
All right, cool.
Okay. All right, guys. Bye-bye.